In this video, we'll talk about the limit of a function. Let's start with the definition. Let f be a function. We say that f at x approaches the number L as x approaches the number a, provided that f at x can be made arbitrarily close to L by choosing x sufficiently close to a. The idea is illustrated in this picture. The x-axis is the horizontal axis, and the y-axis is the vertical axis. We imagine that we're looking at x values that are as close as we like to a. And the closer that the x values are to a, the closer the y values will be to L. We say that f at x can be made arbitrarily close to L. So if L is some y value, we can choose the distance away from L to be as small as we want. And if we do that, we can always find some range of x values that are so close to a that all of the corresponding output values are within that prescribed distance from L. If we can do this, we call L the limit of f at x as x approaches a. And we write it this way: the limit, and then we write x approaches a underneath the limit, so we write lim for limit, and then underneath that we write x arrow a. The limit as x approaches a of f at x is equal to L. We also just write that f at x approaches L as x approaches a. In order for the limit to exist, there has to be exactly one number L to which f at x gets closer and closer as x gets closer to a, no matter which side of a the numbers x are on. In this picture that you see here, the limit doesn't exist, because when x is to the right of a, all of the output values are getting close to m. If we imagine that we're choosing x values and they're approaching x from the right side, so the numbers are bigger, then on the graph we're approaching the point that has coordinates a comma m. So if you're doing that, the y values are getting closer to m. Remember that f at x is a y value. The output values are the y values. So if x is to the right of a, then the outputs are all getting closer to m. On the other hand, if you're approaching a from the left side, then on the curve, you're approaching the point that has coordinates a comma L. And in this case, the y values are approaching L. So that means as the x values approach a, the y values don't approach one number, they approach two numbers. And that means there is no limit, because in order for there to be a limit, all of the y values need to accumulate around that one number that is the limit. Let's look at an example. F at x equals x squared minus 4 divided by x minus 2. Determine if the limit as x approaches 2 exists of this function f at x. And if so, what is it? Well, notice that x equals 2 is not in the domain of f, so that means f at 2 is not defined. However, the limit does exist, and we can get that idea from the picture. We're looking at x equals 2. If you imagine that the x values are getting close to 2, they can either come from the left side, from numbers smaller than 2, or from the right side, numbers larger than 2. If the x values are getting close to 2, then on the curve, you're getting close to this point that has coordinates 2 comma 4. So that means that all of the y values are getting close to 4. So that tells us that 4 is the limit. Well, that's what it looks like based on this picture. Is there any way to prove that exactly? The graph of f at x equals x squared minus 4 over x minus 2 is a line with a hole in it at the point 2 comma 4. And we can see that because we can reduce the fraction that defines f. So if we look at this graph, The graph is the graph of the equation y equals x squared minus 4 over x minus 2. And we can reduce that. If we factor the numerator, that's x plus 2 times x minus 2 divided by x minus 2. The numerator and the denominator have a factor in common, namely x minus 2. So we can reduce this, and we see that y is equal to x plus 2. This isn't the graph of y equals x plus 2. It almost is. It's just that it's got a hole in it. So this is the graph. So the graph is the graph of y equals x plus 2 for x not equal to 2. That's why we have this little bit of hole in here. So what can we determine from this? Well, the limit as x approaches 2 of f at x is going to be the limit as x approaches 2 of this expression x squared minus 4 over x minus 2. When you look at the limit as x approaches 2, that means x isn't actually equal to 2, it's just getting close to it. So that means you're looking at a number which is not 2. So you're not actually dividing by 0 in this expression. So we can just reduce it, and we'll have the limit as x approaches 2. You reduce the fraction, and you end up with y equals x plus 2. So this will just be x plus 2. When you're looking at a limit as x approaches 2, that means x is getting really close to 2. So what are the output values getting really close to? Well, the output values are x plus 2, but x is getting really close to 2. So the output values are getting really close to 2 plus 2, which is equal to 4. So that's how we know that this point here has coordinates 2, 4. So 2 is not in the domain of this function, and 4 is not in the range. There is no value that actually gets 4, because if there was a value, it would be 2, and 2 isn't in the domain. However, the limit as x approaches 2, as x gets close to 2, does exist and is equal to 4. Let's look at another example. F at x equals sine of x divided by x. This function is defined for all values of x except x equals 0. That's why you can see that there's a hole when x is equal to 0. But does the limit as x gets close to 0 of f at x exist? From the graph, it looks like it does. It looks like the outputs are getting really close to 1. As x gets close to 0, coming in from the left side or the right side, the y values appear to be approaching 1. On the graph, we're moving up towards the point that has coordinates 0, 1, or so it appears. So it appears that the y values, the outputs, are getting close to 1. That's how it looks from the graph. We can do some experimental evidence as well. Let's compute f at x equals sine of x over x for values of x that are close to 0. So if you plug in x equals 0.1, 0.01, 0.001, 0.0001, all the while getting closer and closer to 0, you can look at the outputs, which are sine of x over x, and you can see that the numbers are getting very close to 1. And in fact, the more zeros that I put in front of this input, the closer I'll get to 1, the more 9s I'll get here. Similarly, if x is negative, so if it's negative, that means it's approaching from the left. If we look back at our picture, you can see that when x is approaching from the right, x is a positive number, but when x is approaching from the left, it's a negative number. So if you're approaching from the left, you're negative. So you could look at minus 0.1, minus 0.01, minus 0.001, and so on. And the closer that these numbers get to 0, the more 9s you pick up in this output. So it does indeed look like the limit is 1. It looks like the output values are getting closer and closer to 1. Now, unfortunately, seeming like the answer is 1 doesn't actually tell us enough to conclude that it really is 1. We will show later on that the limit is indeed 1, but for right now we can just speculate that it looks like it's probably 1. In our example so far, the function was undefined at the x value we were looking at, but we can talk about limits of functions as x approaches a when f of a exists. So for example, if we look at the function f at x equals x squared minus 3, that's a function that has the graph of a parabola. We could, for example, look at the limit as x approaches 3 of f at x. So in that case, we're looking at this spot here. This is where 3 is. So we're going to look at the output values as x gets close to 3. Now, as x gets close to 3 from the left side, we're moving up the parabola, getting close to a certain point. And if we're approaching 3 from the right side, then we're moving down the parabola towards that same point. Now that point has coordinates 3, 6, because right here, that's a 6. So we can see that as x gets close to 3, as the inputs get close to 3, the outputs, or the y values, get close to 6. So the limit as x approaches 3 of f at x is equal to 6. And that is also the output. 3 is in the domain, and if you compute f at 3, that's 3 squared, which is 9, minus 3 is 6. So in this case, the limit as x approaches 3 of f at x is 6, but that's also the output at 3. F at 3 is defined and equal to the same thing. Now we say that a function f is continuous at x equals 3 when it has this property. When the limit as x approaches 3 is the same value as the function actually at 3, in that case we say that the function is continuous at x equals 3. Broadly speaking, a function is continuous at x equals a if there are no holes, jumps, or gaps when x equals a. The precise definition is in terms of limits. So a function f is said to be continuous at a if the limit as x approaches a of f at x is equal to f at a. One way to think about this is you think about a limit as the values that the function is getting close to. So the limit tells you what output value the function wants to be. The limit as x approaches a of f at x. That tells you what the function wants to be at a. That won't necessarily be the same as the actual output value. So this tells you what it wants to be, the output value, and this tells you what it actually is. And a function is continuous if the limit gives you the same value. So if the function actually attains the value that it wants to attain at a, then we say that the function is continuous at a. Now, if a function fails to be continuous at a point, we say it's discontinuous there. But a function doesn't have to be continuous at a point in order for a limit to exist. In our earlier example, where we were looking at f at x equals x squared minus 4 divided by x minus 2, we saw that the limit did exist. The limit as x approaches 2 of f at x is equal to 4. That limit does exist, but f at x is not defined at x equals 2. So the function isn't defined there, but the limit does exist. So this function is not continuous at x equals 2 because the function isn't defined at x equals 2. But the limit does exist because the function, there's a clear value that the function wants to attain. The function wants to attain 4. It just doesn't because of the way we defined it. We defined it with x minus 2 in the denominator, which means you're not allowed to plug in an x equals 2. We've been looking at examples where limits do exist, but limits don't always exist. The graph below is the graph of f at x equals 1 over x. Now in this case, the limit as x approaches 0 does not exist because 1 over x does not get close to any number as x gets close to 0. F at x equals 1 over x grows arbitrarily large as x approaches 0 from the right side. If I approach 0 from the right, from the positive side, then on the graph, our values are shooting upwards. So that means our y values are getting larger and larger without bound. On the other hand, if we're approaching x equals 0 from the left side, that means the graph is dropping away. So the y values in this case are decreasing without bound. In a case like this, we write that the limit as x approaches 0 with a plus in the superscript of f at x equals 0. So when you write x approaches 0 plus with the plus sign in the superscript, what that means is you're approaching from numbers which are bigger than 0. You're approaching from the right. You should think of this as saying that x is equal to 0 plus something. So in particular, x is bigger than 0. So this notation, x approaches 0 plus, that means x is 0 plus something, or it's bigger than 0. You're approaching from the right. So if x is approaching 0 from the right, then the outputs are, well, we say that the limit is equal to infinity. That doesn't mean that there's some number called infinity that the numbers are getting close to, that the outputs are getting close to. This simply means that the numbers are growing larger and larger without bound. So we say that the limit equals something, but this is just notation, which means that it's growing larger and larger without bound. Similarly, if we're approaching from the left, then we write the limit as x approaches 0 minus. So here there's a superscript with a minus in it. So again, you should think of this as x equals 0 minus something. So in particular, x is less than 0. So the numbers x are approaching 0 from the left side, from over here. In this case, the y values, the outputs, are decreasing without bound. So we say that the limit is negative infinity. Again, negative infinity isn't a number that the limit equals. This is just simply notation, which is a sort of shorthand. It means that the numbers are decreasing without bound. So there isn't an actual limit. The numbers to the right of 0 give you outputs that are growing larger and larger and larger without bound. But if you're looking at inputs to the left of 0, then you're over here. And now the y values, the outputs, are getting smaller and smaller. They're decreasing without bound. Let's look at another example. The function f at x equals the absolute value of x over x has what we call a jump at x equals 0. And you can see that from the graph. If you're looking at values of x which are positive, then the absolute value of x is just going to be equal to x. So if you're looking over here to the right of 0, then the absolute value of x is just x. So f at x is the absolute value of x over x. You're just looking at x divided by itself. So you're going to get 1. On the other hand, if you're looking at negative values, then the absolute value of x is the opposite of x. So you're looking at the opposite of x over x, which gives you a negative 1. So in this case, when your x values are positive, you always have 1. So the limit as x approaches 0 from positive values is 1. But if you're looking at negative values, then all of the outputs are minus 1. If all of the values over here are minus 1, if all of the y values are minus 1, then the y value that they're getting close to is minus 1. So you can see that depending on what side you're on, you're going to get a different number for your limit. So the limit doesn't exist. The limit does not exist because the absolute value of x over x doesn't get close to exactly one number. It gets close to 2 numbers. So in this case, again, we use this notation, x approaches 0 plus. Once again, that means that x is equal to 0 plus something. X equals 0 plus something. So in particular, x is greater than 0, so it's to the right. And if you're to the right, then the absolute value of x is equal to x. So you just end up with x over x, which is 1. Now, on the other hand, if you're looking at numbers to the left of 0, that's the limit as x approaches 0 from the minus side, or x approaches 0 to the minus. So again, this just means x is equal to 0 minus something. but what that really means is that x is less than 0. So if your x is less than 0, then you're on the left. So you're looking at x values that are to the left of 0. And in that case, all of your outputs are minus 1. So we say that the limit as x approaches 0 from the left side of f of x is going to be equal to minus 1. All of the output values to the left are negative 1. So if all of the values actually equal negative 1, then the limit is still going to be negative 1, because the number that they're getting close to is negative 1, because they're actually there. But you can see that the limit depends on what side of 0 you're approaching from. If you approach from the right, you get a positive 1. If you approach from the left, you get a negative 1. So the limit can't exist because the output values don't approach one value, they approach two values. We've been using a certain notation, so let's formally introduce it. If f at x approaches m as x approaches a from the right side, so if x is greater than a, then we write the limit as x approaches a plus. So again, this is a plus something. So that means we're approaching x from larger numbers. X is to the right. So in this case, we say the limit as x approaches a from the right of f at x is m. And you can see in the picture that if x is approaching a from the right, then you're moving along this portion of the graph, and your y values are getting close to m. Now, on the other hand, if you're looking at the left, then you're moving along the graph like so, and so your y values are getting close to L. So in this case, we say that the limit as x approaches a from the left of f at x is equal to L. So this first one, the limit as x approaches a from the right of f at x is equal to m. And the limit as x approaches a from the left of f at x is equal to L. This gives us a convenient test for the existence of a limit. In order for a limit to exist, both the left and right limits must exist and be the same thing. So in other words, the limit as x approaches a of f at x is equal to L if and only if both of the limits from the side are equal to L. So the limit as x approaches a from the positive side, that is, x is approaching a from the right, has to equal L. And the limit as x approaches a from the left also has to equal L. So this is the right-hand limit, because the x's are approaching a from the right side, and this is the left-hand limit. Because the x values are approaching a from the left side. In our earlier example where f at x was equal to x squared minus 4 over x minus 2, in this case the limit at x equals 2 does exist because the left limit and the right limit are both equal to 4. On the other hand, f at x equals the absolute value of x over x, this limit doesn't exist as x approaches 0 because the left limit and the right limit do not agree, they're not the same. So if the left limit and the right limit don't agree, then the limit doesn't exist. Let's look at an example. The following is the graph of y equals g at x. Does the limit of g at x exist as x approaches a for two choices of a, where a is equal to negative 1 or where a is equal to 2? So let's look at this based on the graph. So we'll start with the limit as x approaches negative 1. Does this limit exist? Well, we'll start by looking at the limit as x approaches negative 1 from the left. So that means we're looking at negative 1, and we're going to approach it from the left. So on the graph, you can see that we're approaching this point, which appears to have coordinates minus 1, comma 3. Now we're really interested in what's going on with the y value, and you can see that the y values appear to be approaching 3 in this case. So the limit as x approaches negative 1 from the left appears to be 3. Now, on the other hand, if we're approaching from the right, which is what this means, the limit as x approaches -1 from larger numbers from the right, in that case, what's happening? Well, now we're looking at this graph right here. So if we're looking at this graph, we appear to be getting close to the point with coordinates -1, 4. So in particular, the y values are getting close to 4. The left limit is 3, and the right limit is 4. Those don't agree. So the limit as x approaches -1 does not exist. Or often we just write DNE for does not exist. In order for this limit to exist, in order for the limit as x approaches -1 to exist, the left limit and the right limit have to both exist and agree. The left limit is 3, and the right limit is 4. Those limits do not agree, so the limit doesn't exist. Well, what about the limit as x approaches 2? Now we're over here. So as x approaches 2 from the left, you're moving along the graph towards the point with coordinates 2, 0. So what does that tell you? That tells you that the y values are getting close to 0. What about if you're approaching from the right? Well, if you're approaching from the right, well, then again, you're moving along this curve. And now you're still going closer to the point with coordinates 2, 0. So the y values are still going to 0. So the limit from the left is 0 and the limit from the right is 0. Those two agree. So the limit is 0. Now notice that g at 2 is defined. G at 2 is equal to 5. That's this point right here. So g of 2 is equal to 5. But this is not equal to the limit as x approaches 2 of g of x. Because that limit, the limit as x approaches 2 of g of x, is equal to 0. When you're looking at a limit, you're not actually looking at what's going on at 2. So this is the limit as x approaches 2. You're not actually looking at what's happening at x equals 2. At x equals 2, the output value is 5. But you're looking instead, when you're looking at a limit, you're looking at what's happening nearby. So as x is really close to 2, so just a little bit to the left or a little bit to the right, all of the y values are getting closer and closer to 0. So what the function is saying is, okay, I'm getting close to 2, and it looks like I'm getting closer to 0. It looks like my outputs are getting closer to 0. So the function thinks, as you're taking the limit, the function thinks that the output is going to be 0. But it's in for a surprise when it actually gets to x equals 2, because suddenly it jumps up to 5. So this function is not continuous, because there's a hole there. We approach this example graphically, but we can also approach examples algebraically. Here's another example. Suppose that f at x is a piecewise defined function. It's defined in two pieces. If x is less than 4, then the formula we use is x squared plus c. And if x is greater than 4, then the formula is the square root of x minus c. So the question is there some value of c for which the limit as x approaches 4 of f at x exists? Well, in order to determine that, we need to look at the left limits and the right limits as x approaches 4. So let's start with the limit as x approaches 4 from the left. Now, if x is approaching 4 from the left, that means x is 4 minus something, so x is less than 4. So if x is less than 4, then we're using this top rule, x squared plus c. So for all of the values, as x approaches 4 from the left, you're going to use the formula that's given on the top of this list, x squared plus c, because x is less than 4. So f at x, in this case, is always equal to x squared plus c, because x is always less than 4. If you're looking at the limit as x approaches 4 from below, so in this case, x is always less than 4. So you're going to use this formula where x is less than 4. So it's x squared plus c. So we just write x squared plus c. All right. The limit as x is approaching 4 from below of x squared plus c. Well, if x is getting close to 4 from below, then x squared is getting really close to 4 squared. So this is going to be close to 4 squared plus c, which is 16 plus c. If x is really close to 4, then x squared is close to 4 squared, which is 16. Okay, well, now what about the limit as x approaches 4 from the right? This is x equals 4 plus something, so x is bigger than 4. If x is bigger than 4, then you're using the second part of this formula, which is the square root of x minus c. So f at x, in this case, so this is the limit as x approaches 4 from the right, is going to be radical x minus c. So radical x is the positive square root. So if x is getting really close to 4 from the positive side, then the square root of x, or the positive square root of x, is getting really close to the positive square root of 4 minus c. Of course, the positive square root of 4 is 2 minus c. In order for the limit to exist, then we need the limit from the left, which is 16 plus c, to equal the limit from the right, which is 2 minus c. So we need these two things to equal each other. So we want 16 plus c to be equal to 2 minus c. So if you add c to both sides, you'll get 16 plus 2c is equal to 2. And now we subtract 16 from both sides, we'll have 2c is equal to 2 minus 16 is a negative 14. So divide everything by 2, and then you get c equal to negative 7. So what this is telling us is that the left limit will equal the right limit provided c is equal to negative 7. And therefore, the limit as x approaches 4 of f at x exists provided c is equal to negative 7. We can also look at this graphically, and we have a couple of graphs on this next slide. So the graph on the left is the case where c is equal to 0, and the limit doesn't exist in this case. The graph on the right, on the other hand, is when the limit does exist. And the limit does exist when c is equal to the value that we just discovered, which is negative 7. So in this case, the limit does exist. So if c is anything other than negative 7, you'll have this kind of jump. And when you have a jump, the limit doesn't exist. But when c is equal to negative 7, the two pieces of the graph link up, and then the limit does exist. Now notice that the function is undefined at 4. That's because if we go back to our original definition of the function, so let's go back to the previous slide, you can see that we have a rule for when x is less than 4, and we also have a rule when x is greater than 4, but no rule is given for when x is actually equal to 4. So this function is not defined at x equals 4. So that's why the graph will necessarily have a hole in it. When c is equal to 0 in this picture, we have this jump, but notice that 4 is not in the domain. So 4 does not have an output value associated with it. Even in the graph on the right, where the two pieces link up, the limit does exist when c is equal to negative 7, but the function is not defined at x equals 4. So there's still this hole there, even though the two pieces of the graph meet up there. Let's talk a little bit about infinite limits. So if the values of a function grow larger and larger without bound as x approaches a, then we write the limit as x approaches a of f at x equals infinity. So in this case, we're looking at the graph of y equals 1 over x squared. So the limit as x approaches 0 of 1 over x squared is infinity. Now this limit does not exist. It's just notation. 1 over x squared doesn't approach any one value. It grows larger and larger without bound. It grows larger than any value, so the limit does not exist. If the value of f at x decreases without bound as x approaches a, then we write the limit as x approaches a of f at x equals negative infinity. So here we're looking at the graph of y equals the natural logarithm of x. As x approaches 0 from the positive side, this function decreases without bound. So we say that the limit as x approaches 0 from the positive side, or from the right, of ln of x equals negative infinity. This limit does not exist. We say that the limit is negative infinity, but this is shorthand for saying that the limit does not exist because the function decreases without bound. Notice that this is a one-sided limit. It necessarily has to be a one-sided limit because the natural logarithm of x doesn't include negative numbers in its domain. So you can only approach 0 from the right. You can't approach 0 from the left because that's outside of the domain of the function. But one-sided limits work the same way as two-sided limits. It's just that we consider values of x on only one side. In this case, we're only looking at values of x to the right of 0, but otherwise it's the same. Let's introduce a definition. If the limit as x approaches a of f at x is infinity, or the limit as x approaches a of f at x is equal to negative infinity, then we say that x equals a is a vertical asymptote for the graph or for the function. We also use this terminology for one-sided infinite limits. So, for example, both y equals 1 over x squared and y equals the natural logarithm of x have a vertical asymptote at x equals 0. That's because we have an infinite limit as x approaches 0. On the left graph, for y equals 1 over x squared, we have that the limit is equal to infinity from either side, so we have a vertical asymptote. For this graph on the right, y equals ln of x, we have a vertical asymptote because we have an infinite limit as x approaches 0 from the right. Now, I say it's an infinite limit. It's approaching negative infinity, but we still call that an infinite limit. Now, in both of these cases, the limits don't exist. If the limit is infinity or negative infinity, the limit doesn't actually exist. This is just a shorthand notation, which means that either the values are growing without bound or they're decreasing without bound. We can also talk about limits at infinity, that is, as x grows without bound, or as x decreases without bound. So if the values of f at x get closer and closer to some number L, that is to say the distance between f at x and L gets arbitrarily small, as x grows larger and larger without bound, then we write that the limit as x approaches infinity of f at x equals L. Now this doesn't mean that f at x actually takes on the value of L. It might, but it doesn't need to. It just means that the distance between f at x and L gets arbitrarily small as x grows larger and larger. Similarly, if the values of f at x get arbitrarily close to L as x decreases without bound, then we write that the limit as x goes to negative infinity of f at x equals L. In either case, we call y equals L a horizontal asymptote. And once again, x doesn't actually get to infinity or negative infinity. This just means that x is growing without bound, or x is moving to the right without bound. And this one, x approaches negative infinity, just means that x is moving to the left without bound. Let's look at a graph. The graph of f at x equals 1 plus 1 over x minus 2 has a horizontal asymptote at y equals 1 and a vertical asymptote at x equals 2. So if we look at the limit as x grows larger and larger without bound, that means we're moving to the right. And you can see from the formula f at x equals 1 plus 1 over x minus 2 that if x is growing larger and larger, then this term, 1 over x minus 2, is going to become arbitrarily small, because as x grows larger and larger, the thing in the denominator is becoming huge, and therefore 1 over that denominator is becoming small, negligible. So as x goes to infinity, this term 1 over x minus 2 becomes negligible, almost nothing. So that means that as x grows arbitrarily large, the output values get closer and closer to 1. So that's why we have that the limit as x approaches infinity of f at x is equal to 1. Now the same is true as x gets closer to negative infinity. Of course, when I say x gets closer to negative infinity, it's not actually getting close to anything. It's just becoming more and more negative. It's moving to the left on the graph without bound. Now, as x moves to the left without bound, then you're still looking at 1 over some number which has a very large size, albeit negative. So this is going to be 1 minus something close to 0. So this 1 over x minus 2 will be a negative number which is very close to 0. So you're going to have 1 minus something close to 0. So again, the output values are getting close to 1. And so that gives you this horizontal asymptote. We also have a vertical asymptote at x equals 2 because as x gets closer to 2 from the right, we are adding something which is arbitrarily large. But as x approaches 2 from the left, then this is a negative number which is arbitrarily large in size, but it's a negative number. So you end up with 1 minus something infinitely large. So that's why you have this vertical asymptote at x equals 2. Let's look at another example. The graph y equals the inverse tangent of x has horizontal asymptotes y equals pi over 2 and y equals negative pi over 2. So as x goes to infinity, that is, as you move further and further to the right, the inverse tangent gets closer and closer to pi over 2. As x moves to the left, then the graph of the inverse tangent gets closer and closer to the line y equals negative pi over 2. And that's what it means to be a horizontal asymptote. It means that as your graph moves further to the right or to the left, the graph itself gets close to these horizontal lines. We know that the inverse of tangent has horizontal asymptotes at y equals pi over 2 and y equals minus pi over 2 because the graph of tangent has vertical asymptotes at x equals pi over 2 and x equals minus pi over 2. Remember that you obtain the graph of the inverse by reflecting through the line y equals x. So your vertical asymptotes become horizontal asymptotes. The graph y equals e to the x has a horizontal asymptote y equals 0. That's because the limit as x approaches negative infinity of e to the x is equal to 0. Notice that the limit as x approaches infinity of e to the x is infinite. That's because this grows without bound. Now there is no asymptote associated with this kind of limit. The limit as we're moving to the right doesn't exist because e to the x grows larger and larger without bound. The horizontal asymptote for y equals e to the x corresponds to a vertical asymptote for y equals the natural logarithm of x. Again, that's because you obtain the inverse ln of x by reflecting the exponential function through the line y equals x. This is the line y equals x here. Y equals x. E to the x has a horizontal asymptote, which is the x-axis. But if you reflect the graph y equals e to the x through y equals x to get the inverse, then you don't just reflect the curve, you also reflect its horizontal asymptote. So if you reflect the horizontal asymptote, which is the x-axis, you get a vertical asymptote, which is the y-axis. And this vertical asymptote is an asymptote for the inverse function, which is y equals ln of x. The graph of y equals sine of 1 over x has a horizontal asymptote y equals 0. Again, the x-axis is y equals 0. Because if you look at the limit as x approaches infinity of sine of 1 over x, you get 0. So if you look at your graph, as x moves further to the right, this graph gets closer and closer and closer to the x-axis. Similarly, as x goes to negative infinity, that is, as x moves further and further to the left, your graph gets closer and closer to the x-axis. So the limit as x approaches negative infinity of sine of 1 over x is equal to 0. This might not be immediately obvious. The basic principle at work here is that if you have sine of a very small number, then sine of that small number is approximately the same as that small number. So since x is getting very large in size, either moving towards infinity or negative infinity, so the size, the magnitude of x is very large. So 1 over x is very close to 0. So sine of a number which is very close to 0 is approximately equal to that same value. So if theta is very small, then sine of theta is approximately theta. So sine of 1 over x in this case is approximately 1 over x. So that's why these limiting values are 0. So that means we have a horizontal asymptote y equals 0. Notice that the curve actually crosses the asymptote. It's fine that the graph crosses y equals 0. When you say that a function has a horizontal asymptote, what you mean is that its graph is getting close to the horizontal asymptote as x moves to the right or to the left. It just means that the graph is getting close to that asymptote. But that doesn't mean that it never crosses it. It just means that as you move further and further away, eventually it's getting closer and closer. But it might actually cross the horizontal asymptote an infinite number of times. And in fact, it does that here. This graph oscillates wildly around x equals 0. So in fact, this graph crosses its horizontal asymptote an infinite number of times, but that's fine. Now this does bring up an interesting question. Does the function f at x equals sine of 1 over x have a limit as x goes to 0? Now it certainly doesn't include 0 in the domain. You're not allowed to put 0 in the denominator here. So x equals 0 is not in the domain of this function. But does it have a limit as x approaches 0? Well, let's zoom in. If we zoom in on the graph near the origin, you can see that this graph is just oscillating wildly. So the limit as x approaches 0 of sine of 1 over x does not exist as x goes to 0. The graph does not approach one number as x approaches 0. In fact, the graph approaches every number on the y-axis between -1 and 1. So in order for a limit to exist, all of the outputs need to approach one number. But in this case, the outputs approach all of the numbers between -1 and 1, infinitely many numbers. So that means the limit does not exist.